So now we come to the inverter and grid interface. So there's a standard EN 61000, so 61000-6-1, and then the year 2007. It describes the electromagnetic compatibility, so this immunity for residential, commercial, and light industrial environments. Then you have here some differences between industrial, residential, and so on. Emissions, so this is the emission on radio frequencies and so on. So there's no radio disturbance by that. Then this is more interesting here. You have here just for the information technology equipment. So radio disturbance, yes, that was the upper one also. And then you have the 50178. This is the standard for electronic equipment used in power installations. Then you have a specific one as a 61683 for photovoltaic systems. And this is also, as I mentioned, the UE norm, the procedure for measuring power efficiencies. This is also very important for description the characteristics of the utility interface. So you have to, because these are sometimes changing depending on when the next edition, you have to make sure that you have the latest standard, and this has to be in agreement with the requirements. Sometimes the utility, they stick to an older requirement. So an older year, you have to just make sure that you can use the latest requirement, or whether they require that you stick to an older standard, which was usually not often the case. Safety of power converters for use in photovoltaic system, and islanding prevention measures for utility. So if the grid is switched off, what happens then? This has to be certified by that norm 62116. Usually the power output, the voltage output by the inverters limited, 600 or 800 volts, and you want to interconnect it to the mid-voltage grid or even the high-voltage grid, you have to apply a transformer, so which transforms, for example, from 600 volt to 10,000 or even 20,000 volts. And this is a selection checklist for the transformer. So you have here the transformer has to be suitable for the project size. It has to comply with the national grid regulations. You have to have a supplier identification and track record checked. As I mentioned before, the minimum certification obtained. I have a product warranty terms and conditions in line with the market standards. While the bank is usually financing the power plant as a whole, they always take the worst conditions, so they take the lowest warranty. So you have to make sure that all components have the required warranty periods. So for example, 25 years. And so you have to check that the warranty of the transformer is also that. Usually electronics don't have that. Maybe you have to purchase an extra warranty insurance. Suitable for the environmental conditions, same as before, inverter and modules. So outdoor, indoor, ambient temperatures and altitude, maybe also dust, because when the transformer is artificially ventilated, there can be some dust accumulation, or altitude could be either temperature change or ultraviolet radiation. And also the efficiency plays a role. It's usually not a big issue, because most modern transformers, they just lose 0.5% or so. It's usually not a big deal breaker. And a load and no load issue in line with the market standards. Mounting structure. So the mounting structure also the same, supplier identification and track record checked. Usually these are custom, or often, not always, but often custom made by local companies. So it's quite hard to check the quality control of the manufacturer, or you purchase a pre-fabricated module mounting structure and so on. Also there's some certification issues. The product warranty terms and conditions in line with the market standards. And it has to be suitable for the environmental and ground conditions. For example, thermal expansions, marine environment, soil acidity, and so on. Also, if you combine different materials, for example, you have the foundations on concrete, then you put in a steel bar, and on the top there is aluminium, and there could be some severe corrosion between these two metals. If there's, for example, acid rain and so on, then they corrode very quickly. Then the general design checklist, quite obvious, the tilt angle and orientation of the PV array suitable for the geographical locations, or even if you want to, for example, produce more power during winter time, you choose a higher tilt angle. or you put it more towards western, you have more western orientation, so it's more producing in the afternoon and so on. As we already heard in the lecture, so the interrow distance is relevant for the shading. So you have to choose an adequate interrow. This also depends on the height due to the tilt angle and the size of the modules and so on. And the usual location there. When it's close to the equator, then sure, the sun is always more perpendicular. If it's more towards the poles, then during winter time you have more shading, and then you have to increase the distance between the rows. Shading of obstacles or nearby projects, this could be some buildings or trees and so on. We have to also take into consideration if you have young trees there, in 15 or 20 years the trees may grow and then cause shadowing then. But some simulations program like PVSol, they included that. You give in the type of tree and it already calculates this, the future size of the trees and the possible shading. The PV string size suitable for inverter under the site environmental conditions. As I mentioned already, we had it also in the lecture and made an exercise about it. So if you have very cold conditions, then voltage may increase, and in order to keep within the standards, for example, you have to keep below 1000 volts under all conditions, and so you only can interconnect a certain amount of PV modules in series. For example, 21 module. If you would have 22 modules, even under standard test conditions, would be below 1000 volts. But if you have very low temperature, for example, very cold winter morning with -10 or -20 degrees, then voltage increases and you then past this 1000 volt limits, then the PV power plant is out of certification. And this is to be checked. It even may destroy an inverter depending on the tolerance of that inverter, but there could be even some destruction of some components. Also, you have to make sure that the possible operating conditions stay within the range of the maximum power point tracker of the module. As I mentioned before, the transformer has to be correctly sized. Combiner boxes, so you have to make sure that no humidity enters and no dust enters. So there's the IP rating, for example, IP68 or something like this. This makes quite sure that no rain and no dust can come in. The DC and the AC cables are sized correctly. We did this already in the exercises. The low voltage and high voltage protection equipment, so that means fuses. Fuses also we have to distinguish between DC and AC. The switch gears, same issue, and circuit breaker, same issue. The suitable grounding or earthing and lightning protection designed for the site-specific locations, also the national requirements. Civil works, so that's the foundation and the drainage for rain and so on. So you have to make sure that no water enters the hut where the inverter is and so on. So you have to make that sure. And depending on the local, if you have in the desert, you have less problems. But if you have an area where you have a monsoon period, this can cause some serious problems. The monitoring system, so you want to check whether your modules and your whole system is performing well. You have to make a monitoring system. Mentioned when we discussed about microinverters, they allow even monitoring on on a single module level. If you have strings or even a central inverter, it's hard really to distinguish which part of or which exactly component failed if there's some problems in the power plant. In a security system, you have to make a fence perhaps there so nobody can steal modules, or it could be some vandalism and so on. This depends on the requirements by the insurance provider. And it has to be accepted by them. Sometimes a really expensive project, they send someone there to check that. Now we come into the phase of detailed planning. So first you start with the first chapter, Solar Resource Assessment Checklist. So you have a variety of solar resource datasets we'll discuss a little bit later. You know already from the first lecture. Best would be if you have at least 10 years of data. Sometimes you don't have this data available, so sometimes you have only from 1 year, and you have to check whether this changes something or still accepted by the utility or by the one who is, or by the banks and so on. Can use satellite-derived data or data interpolated from ground-based measurements. Sometimes there is a ground-based meteorological station in some distance, and you can interpolate that. Usually the programs do that already. For example, the Meteonorm software is able to do that, so it takes several close-by measurement stations there and interpolates that. Then you have to the site adaptation, the calibration of satellite data be used. We found out that satellite data differs because you can only see the reflected part from the ground, and we found some years ago some up to 20% difference in that. Maybe this improves. This depends also on the site location and so on. So best is to calibrate it, to put a pyranometer there and check for that time point the data given by the satellite and see whether these two irradiance values agree to each other. Some algorithms have been placed to convert the global horizontal irradiance. That's usually what you measure, data you get from ground-based measurements from meteorology station, but also from satellite data. They don't have data really for tilted areas, and so this is interpolated by some algorithms. Very important to do an uncertainty analysis. How much are the possible errors? How much is the tolerance by the pyranometer? What are the tolerances by the algorithms and so on? Here, the different software to do a solar resource assessment. So there is SolarGIS. This is available between 60 degrees north and 50 degrees south with a relatively high resolution of 250 meters. And it's calculated from satellite data and atmospheric data and digital terrain models. Solar resource data are available from the years 1994, 1999, or 2006, depending on the region and so on, with a time resolution of 15 minutes. This database has been extensively validated. That's important for more than 180 locations globally. This 3-tier don't know so well, so this is also quite similar. Here you see 120 reference stations across the globe with a standard error of global irradiance of 5%. HelioClim, this is also from commercial satellite derived. There's not so much given about the tolerance. What is very often used is the Meteonorm database. This is specially made for photovoltaic application. So you can even have some tilt angles there and they calculate the irradiance on the tilt angle and divide between direct and diffuse irradiance in case you have concentration things, and you can look up on the website. So what's the actual, I think the actual version is 8.0. This commercial free software is from the NASA surface meteorological energy data. So you have here data of a grid of 100 by 100 kilometers, so it's much more raw than SolarGIS, which is 250 meters by 250 meters, but it's for free, so it's also quite good, evaluated for 22 years. It's good for preliminary feasibility studies, because for detailed they have too low spatial resolution. Then the PVGIS, so that's from the European Union, it's for free. It's for Europe and Africa, as far as I know. And they included also some temperature models. So they also include the possible yield of PV panels. And so they provide maps where you find exactly the energy output per kilowatt installed of a conventional photovoltaic crystalline PV modules. So that's quite comfortable. Okay, resolution is better than from NASA, 2.5 kilometers only, but not as good as SolarGIS. But it's quite helpful, and the best thing is it's for free. But if it's outside, so in the Americas or somewhere in Oceania, it's not really suitable. But for Africa and Europe, it's a very good option, and Middle East. So now the operation and maintenance contracting checklist. So a legal and technical advisor engaged to advise on form of contract. The O&M contractor is suitably experienced on a similar scale, planned and familiar with the technology. The performance guarantees included to allow owner to claim liquidated damages, LDs, in the event of low ability or low performance ratio. Payments are made to the contractor in arrears to allow for deduction of any LDs over the corresponding period. LD's size to be a genuine part of pre-estimate of losses likely to be occurred. Rules of spare parts management are clearly defined. Contractor is responsible for replenishing stock and ensuring original level is maintained, and the rules for subcontracting is clearly defined to ensure principal contractor that he is fully responsible for all subcontractor works. And the O&M contract requires the contractor to maintain all equipment in line with the manufacturer guidelines to ensure that all equipment warranties remain valid. That's also important. If you modify something, then the warranty may not be valid anymore, and this is a serious issue. Preventative maintenance regime defined in a contract is comprehensive, helping to minimize the need of corrective maintenance. Preventive maintenance, you usually don't have to switch off the power plants. It's quite foreseeable, but what happens if you have corrective maintenance, something happens and you don't know which component has to be substituted, and it takes more time, and during that time you also lose energy yield and money. Now we come to the construction phase checklist. So required, we have a contract fully signed and reviewed by a technical advisor covering all possible interfaces. Design documentation completed. Detailed program of works is completed. The quality plan is completed. The health and safety plan is completed. The monthly reporting is in place. All consenting, permitting, and financial requirements are in place. Commissioning and testing plans as agreed by all parties, detailing requirements and any tests needing witnesses or sign-off. Recommended. So interface matrix are drawn up, so it's more easy to overview the possible interfaces. Deliverable schedules prepare for all documentation, so it makes also much more easy to handle. A weekly look-ahead program is in place. Risk register detailing all potential risks and mitigation measures in place. Environmental plan completed. Monthly report structured completed. Matrix detailing the requirements and due dates prepared. What are common mistakes? So module installation, there could be an inadequate number of clamps used or incorrect positioning, resulting in reduced module bearing load capacity. Usually the positioning of the clamps, also the type and the area of the clamp, is given in the module data sheet. If you modify from that, also the warranty may not be valid anymore. This is what I mentioned. So modified or wrong type of clamps. So there could be an inadequate spacing between the module, compromising integrity of the fixing and leading to invalidation of the warranty. Module clamp bolts initially hand tightened and then tightened to the correct torque after period of delay. There's a risk that strong winds can blow the modules off the structure if a time lag between assembly and tightening is too long. The tightening of bolts should occur shortly after assembly. Over tightening of clamps, so some don't have a torque limiting tools there, and they may destroy the clamp or even damage the modules. So for example, the coatings. Damaged or scratched modules due to poor installation technique. The front and rear surface modules should not come into contact with a support structure. This is also due to the electrical safety. It's given that the module can be only fixed via the module frame, and it really stays away from any metallic material, especially the back part. Mounting structure. So as I mentioned already, dissimilar metals are not insulated from each other, leading to material incompatibility issues in the form of galvanic corrosion. Isolation solutions such as neoprene pads can be used. Deformation of the mounting structure during piling process, compromising galvanization or structure. Piles installed out of position, leading to piles and steel sections being forced or bent out of alignment in order to line up with framing sections. Civil works, poor dust suppressions are leading to excessive accumulation on dirt of modules. Missing or delayed perimeter fencing leading to animal or human intrusion. A fence should be installed prior to construction commencing. Drains becoming blocked with silt during the earthworks. There could be some flooding then. Drains are becoming blocked. Yes, this was before. And inadequate surface water run management during construction, leading to delays caused by flooded or waterlogged sites. Excessive load-bearing capacity of exiting public tracks, causing damage. Lack of leveling works after installation. The integrity of the controlled environment within equipment, enclosures or housings can be compromised if not installed correctly. Common issues include unused glands not sealed or replaced with dummies, unsealable cable conduits, damaged or missing gaskets on entrance doors, unsealable cable trenches leading to inverter housing, so the inverter can be even flooded. A water ingress due to any, all of the above, leading to a humid atmosphere causing corrosion damage to electrical components. Environmental monitoring. Incorrect positioning of the environmental monitoring equipment can lead to inaccuracy during a performance assessment. The most common reasons for these inaccuracies are pyranometers are not positioned at the same tilt angles of the modules. As I mentioned, you could apply an algorithm, but it's not very accurate, so you have inaccuracies there. A pyranometer subject to shading, dust accumulation, and moisture ingress, causing a reporting of elevated performance ratios. It's quite interesting. So if the pyranometer is shaded or has a dust accumulation, you do not see the problem immediately because you perceive reduced irradiance, but still acceptable power output. You think your system is performing very well. Cable management. Cables crossing over sharp edges or mounting structures without suitable padding, insufficient labeling of cable endings, long unsupported spans due to an insufficient number of cable ties, cable banding radius is too tight. This could lead to breakage of the insulation or even of the core of the cable, so the copper and so on. Inadequate cable burial depth. Inadequate conduit cable protection, signage, basic information requirements which are often omitted include general health and safety requirements including emergency contact numbers, a lack of warning labels on electrical components. So if there's high voltage, you have to make that clear by labels. Lack of warning label on perimeter fence, so you have to make clear that nobody can enter, or if you have an electrical fence, you have to advise that. Support structure identification labeling. Spare parts. The permanent storage of spare parts is often not available when such components are delivered to the sites, leading to damage from poor temporary storage conditions. Documentation's actual plan of sometimes the plan is modified and you don't have an actual version. That include all components which are on site. So the detailed wiring plans, including all the properties of the wire, such as flexibility of the wires, UV stability, thicknesses, and material of the conductors. So it could be either copper or could be even aluminum and so on. Also backup. So maybe these plans get stolen or get lost or burned or whatever. So you have to make sure that you get backup because they are really important. Here are some hints for the documentation. So what you have to have for the array, so this is a module types, the number of modules, the number of strings, modules per string, the PV string information, so string cable specifications, the size and type, string overcurrent protective device, the fuse or a diode type, voltage current, blocking diode type, so usually call it string diode. Nowadays it's not often anymore necessary, but formerly it was required. Array electrical details, so the array main cable specification, the size and the type, array junction box locations where it's applicable, the DC insulator type, location and rating, voltage and current, array overcurrent protective device where applicable, type, locations, rating. We did this already in the exercise a bit about the dimensioning of the cables. Earthing and protection devices, so details of all earth and bonding conductors, size and connection points, details of array frame equipotential bonding cable where fitted, details of any connections to an existing lightning protection called LPS, details of any surge protection device installed. Both AC and DC lines include location, type and rating. Usually these are installed either close to the inverter or as connection box, as we saw in the lecture. The AC system, so here you have the AC isolator location, type and rating, AC overcurrent protective device location, type and rating, residual current device location, type and rating, and so on. Grid connection details and grid code requirement, that's really important. This has to be in agreement with the utility. Data acquisition and communication system. So this is data for the communication protocol, a wire regment, sensors. I would add here also passwords and so on. So here you see such a structure. Here you have here the PV array, then the low voltage to mid voltage transformers. Then they have the mid voltage collection switchgear, and then you may go to the high voltage, and you need a high voltage transformer, and then here you are at the grid. These are the voltage levels. So usually high voltage is above 33 kilovolt, and mid voltage is from 1000 volt to 33 kilovolt. And low voltage is below 1000 volts, so this is usually where you interconnect your PV power plant. There is some discussion whether this should be changed to 1500 or even 2000 volts. Here you see the operation, the monitoring optimization. So you see the meteorological sensors, most important the irradiance sensor, but also the temperature sensor and wind speed and wind direction. Then you have operation data of the inverters, the meter, feed-in meter. Sometimes you have a DC meter also, the power transformer and the grid. And this SCADA system is called a system controlled and data acquisition system. It provides real-time data, but also historical data, alarms. In case there is a problem, it sends a SMS to an operator or email or a fax, logs some events. You have here the monitoring sensor, so you have here a connection to the sensors either by DSL or a wireless via the GSM network. And then from the monitoring sensor go via internet, and then you can basically in any part of the world you can check that via the web interface, monitoring visualization. And usually also banks are quite interested in that to see how well their investment is performing. Performance optimization. So the loss, and then we talk about mitigation measures to optimize performance. So in case of shading, so you have to relocate or choose locations without shading obstacles, ensure that the plant has sufficient space to reduce shading between the modules, which we discussed already twice here, and have a robust operation and maintenance strategy that removes the risk of shading due to vegetation growth. So you have a gardener there on something like this who cares about that the vegetation isn't causing any performance issues. The incident angle, anti-reflective coating, textures glass, and so on. Tracking low irradiance, so you choose modules which offer good performance at low irradiance level. That's usually if you have a high RP, this bypass resistor. So if it's really high or best non-existent, you have quite a good low irradiance performance. Module temperature. Choose module with an improved temperature coefficient. That's often not possible because a crystalline module is almost the same in the vicinity of minus 0.4% per Kelvin. But you can take care on a good ventilation and a good distance to the ground or to the roof, and this helps to lower the operating temperatures. The soiling, choose a module less sensitive to shading. Okay, with the soiling, this is same as shading. It can lead to some problems, so just if you have enough bypass diodes, this helps. Ensure suitable operation maintenance contract that includes an appropriate cleaning regime for site conditions and module quality. We discussed this already with a low tolerance or positive tolerance. Yes, it's for the banks, as I told you, they always take a look at the worst case, and if there is no, if you have a zero tolerance to the lower part and just positive tolerance, then they take the number plate value for the power under standard test conditions. Module mismatch, so you sort the module with similar characteristics in the series strings. When possible, avoid the partial shading of a string. Avoid variations in module tilt and angle and so on in the same string. If you use module inverter, this isn't a big problem. DC wiring resistance, we calculated already in the exercise. This also for the inverter performance. Yes, you have the high efficient inverters and they have to be correctly sized. AC losses, also the sizing of the cables and so on, and high efficiency transformers. Plant downtime, that's important, that you have to really make sure that the operation and maintenance team is quickly there and allow a very quick repair of the power plant. So you have to make sure that they have spare parts for it available quickly, so you don't have to wait for weeks until you get a spare part to keep the power plant constantly running. Grid availability, it could be also an issue in some countries. A grid is failing and so you can't feed anything in the grid, and sometimes you don't even get money for that. So also the grid has to be stable and has strong and has the potential to absorb the PV power. But usually the utility is taking care of that. Degradation, so sure you choose modules with a low degradation rate and a linear power guarantee. So you have a guarantee, for example, after 25 years, the module is still able to deliver 80% of its initial power under standard test conditions, or even better. A maximum power point tracking, yes, you have to choose high efficient inverters. Can add to this that they even fast tracking and have a global tracking. Sometimes if you have shading, there could be 2 maximum power point on the IV curve of the modules, and has to find both and then select the actual power point which offers most of the power. So on. Remember when I talked about this in the bypass diet lecture, how the IV curve look like, and the maximum power point tracker has to be able to deal with that. Curtailment of tracking, so ensure that the tracking systems are suitable for the wind loads to which they are subjected. That was it. So most of this part I took from Project Developer's Guide, Utility Scale Photovoltaic Power Plants from the International Finance Corporation. That's a part of the World Bank Group from 2015. Usually if you take care on the required checklist, there shouldn't be a problem in realizing your project. Thank you very much.